So we overlap at Stanford. I looked at your bio. I graduated at undergrad in '92.
Oh, okay. Did you take physics?
Yes, I did. Pre-med.
Oh, okay.
So I took whatever the 20 series back then. Yeah, because I started there in the fall of '88. I loved it there. Perfect day. Is that what you tell people? So is there anything you want me to say about the basic things? Or you just want to get into it?
Physics for poets? So Berkeley doesn't have a physics. Oh. This is
So we overlap at Stanford. I looked at your bio. I graduated at undergrad in '92.
Oh, okay. Did you take physics?
Right. Yes, I did. Pre-med.
Oh, okay.
So I took whatever the 20 series back then. Yeah, no, for me personally, I don't like the long introductions. It was like, here, it's the yeah, because I started there. All right, so I'll keep it short and sweet, and I'll let you get into it. I loved it there. Perfect day. Is that what you tell people? So is there anything you want me to say about the basic things? Or you just want to get into it?
Physics for poets? So Berkeley doesn't have a physics. Oh. This is
So we overlap at Stanford. I looked at your bio. I graduated at undergrad in '92.
Oh, okay. Did you take physics?
Right. Yes, I did. Pre-med.
Oh, okay.
So I took whatever the 20 series back then. Yeah, no, for me personally, I don't like the long introductions. It was like, here, it's the yeah, because I started there. All right, so I'll keep it short and sweet, and I'll let you get into it. I loved it there. Perfect day. Is that what you tell people? So is there anything you want me to say about the basic things? Or you just want to get into it?
Physics for poets? So Berkeley doesn't have a physics. Oh. This is
So we overlap at Stanford. I looked at your bio. I graduated at undergrad in '92.
Oh, okay. Did you take physics?
Right. Yes, I did. Pre-med.
Oh, okay.
So I took whatever the 20 series back then. Yeah, no, for me personally, I don't like the long introductions. It was like, here, it's the yeah, because I started there. All right, so I'll keep it short and sweet, and I'll let you get into it. I loved it there. Perfect day. Is that what you tell people? So is there anything you want me to say about the basic things? Or you just want to get into it?
Physics for poets? So Berkeley doesn't have a physics. Oh.
So we overlap at Stanford. I think I graduated undergrad in '92.
Oh, okay. Did you visit?
Right. Yes, I did. Right. Pre-med. So I took classes. Yeah, no, I for me personally, I went like along with introductions as a kid. Yeah, because I started there. All right, so I'll keep it short and sweet, and I'll let you get into it. I love it there. Perfect. Is that what you're telling me? So is there anything you want me to say about the basic thing? You just want to get into it?
Physics for poets? So Berkeley doesn't have a physics. Oh.
This
This is
So we overlap at Stanford. I think I graduated undergrad in '92.
Oh, okay. Did you visit?
Right. Yes, I did. Right. Pre-med. So I took classes. Yeah, no, I for me personally, I went like along with introductions as a kid. Yeah, because I started there. All right, so I'll keep it short and sweet, and I'll let you get into it. I love it there. Perfect. Is that what you're telling me? So is there anything you want me to say about the basic thing? You just want to get into it?
physics for poets? So Berkeley doesn't have a physics. Oh. This is
So we overlap at Stanford. I think I graduated undergrad in '92.
Oh, okay. Did you visit?
Right. Yes, I did. Right. Pre-med. So I took classes. Yeah, no, I for me personally, I went like along with introductions as a kid. Yeah, because I started there. All right, so I'll keep it short and sweet, and I'll let you get into it. I love it there. Perfect. Is that what you're telling me? So is there anything you want me to say about the basic thing? You just want to get into it?
There is physics for poets? So Berkeley doesn't have a physics. Oh. This is
So we overlap at Stanford. I think I graduated undergrad in '92.
Oh, okay. Did you visit?
Right. Yes, I did. Right. Pre-med. So I took classes. Yeah, no, I for me personally, I went like along with introductions as a kid. Yeah, because I started there. All right, so I'll keep it short and sweet, and I'll let you get into it. I love it there. Perfect. Is that what you're telling me? So is there anything you want me to say about the basic thing? You just want to get into it?
There is physics for poets? So Berkeley doesn't have a physics. Oh.
Toy with his assignment. Testing 1, 2.
So we overlap at Stanford. I think it's about, I graduated with undergrad in 92. Yes, I did. Pre-med. So I took, this 20 series. Yeah, no, I personal algorithm Yeah, I started there. Right, so I'll keep it short and sweet. And I'll let you get into it. I love it there. Perfect. Is that what you're telling me? So is there anything you want me to say? You just want to get into it.
There is five. Toy with his assignment. Testing 1, 2.
So we overlap at Stanford. I think it's about, I graduated with undergrad in 92. Yes, I did. Pre-med. So I took, this 20 series. Yeah, no, I personal algorithm Yeah, I started there. Right, so I'll keep it short and sweet. And I'll let you get into it. I love it there. Perfect. Is that what you're telling me? So is there anything you want me to say? You just want to get into it.
There is five. Toy with his assignment. Testing 1, 2.
So we overlap at Stanford. I think it's about, I graduated with undergrad in 92. Yes, I did. Pre-med. So I took, this 20 series. Yeah, no, I personal algorithm.
Good afternoon, everybody. Hello? Clap one time if you can hear me. Oh, I'm not on? Douglas says I'm on. Good afternoon, everybody. This is one of the final events of the Fall Staff Appreciation Week. Thank you for your participation. Thank you for coming to today's lecture. Thank you also to the folks who are online. This is part of our appreciation of staff. We don't appreciate staff enough. And part of my job, and in my job description, is to be an advocate for staff. So I've been here for 2 months, and I'm doing as much as I possibly can to advocate for staff. And so that means when I go to meetings with my boss and people above my boss, I am unashamed about advocating for the interests of staff. So participate in your organizations, make your message heard, make sure it's right, and I will advocate on your behalf. For example, this morning we were having a meeting, we were talking about parental leave for staff. This is something that's important to staff. This is something that's important to the chancellor. So through your advocacy, things do happen. So that being said, I want to introduce our speaker, Bob Jacobsen, Professor of Physics, Dean for Undergraduate Studies, College of Letters and Science. Bob didn't want me to say a whole lot more than that. He's got a lot of information to share with you, and from what I've heard from those who've heard him speak before. Good afternoon, everybody. Bob. Hello? Clap one time if you can hear me. Oh, I'm not on?
So
Douglas says I'm on.
the title I was
Good afternoon,
given
everybody. This is
was
one of
to
the
talk
final
about a
events
course,
of
Physics for Future
the
Presidents,
Fall
and the
Staff
physics that's in it.
Appreciation Week. Thank you for your
But I want
participation. Thank you for
to,
coming
like
to
all
the
good
lecture.
teachers, I want to make sure you understand the outcomes that I'm intending.
This is
And one of
part
the
of
outcomes that
our
I'm intending is
appreciation
that
of
you
staff. We
understand
don't appreciate
just
staff
how
enough.
important
Part of my
the
job
people
when
of Berkeley,
my
including
job
all of
description is
you
to
and
be
the
an
people who are
advocate for
online
staff.
who are making
So
me
I've
very
been here for
nervous
2
because I
months, and
can't
I'm
see
doing as
you,
much as I possibly can to advocate for staff.
are
So
to the
that means
student
when I go to meetings
experiences
with my
that
boss,
make all the
people
difference
above
to
my boss,
Berkeley.
I am
Although we
initially
haven't
honored
had
to
a
have
president
the
yet
staff.
come
So,
from Berkeley. We
it's a
have
great
had a
organization.
Chief
Make your
Justice.
message heard. Make
Toy with
sure
her
you
son
write
plays the
out
most
as
recent
a
Captain
for
Kirk,
that.
which is almost as important.
Another
John Cho, another actor, two very, very rich people.
This is important to staff. This is something that's important to the kids.
Someone who
So
was
those
one of
are
the very
advocacy,
first
things
women
like that.
aviators and
So,
is likely to have
that
the
being said, I want to
Oakland
introduce
Airport
our
named
speaker,
after her
Bob
shortly.
Jacobsen.
Someone who I'm quite sure did not study physics at Berkeley.
Undergraduate Studies, College of Letters and
Two
Science.
well-known correspondents, including the first foreign Pulitzer Prize winner and two governors.
Those who've heard him speak
So
before.
conceivably, two
Everybody.
governors is like 3/4 of a president or something.
Hello.
So we're making our way there.
Clap one time if you can hear me.
The context for this is a course called Physics for Future. The title I was given was to talk about a course. And we're going to talk about the physics, we're going to talk about the ideas that's in it. But I want to talk about how I want to, like all good teachers, the idea that Berkeley is an evolving place where we all work together to impart the information that we have, but also develop new learnings and new understandings as we go along. Here are some of the physics professors who have been well known for their teaching in the past. Apparently the further back in time you go, not only do you become in black and white, but you also wear jackets and ties. This is Oppenheimer, and this is Teller, two famous physicists who are known by their last names. This is our George Smoot. This is a great picture because this is him teaching a lower division class on the day that he won the Nobel Prize. And this is Irfan Siddiqui, our most recent winner in physics of the Distinguished Teaching Award, who is disproving the fact that you have to be in black and white to wear a jacket. So Teller is a very interesting character. He was the science advisor to 6 presidents. This is a picture of him with President Kennedy, and that's Glenn Seaborg. There's a comment in Doe Library from Glenn Seaborg where he says that one of the things he thinks is most, I forget whether it's interesting or elegant or something like that, is that his name is an acronym for Go Bears. And President Kennedy, of course, and this is Teller in the middle, and this is the last one, the last president that he was an advisor to. He created the Space Sciences Lab, which are the people up the hill who just launched a satellite 10 days or 2 weeks ago, right after a brownout, which is a wonderful thing. He brought Kennedy to Berkeley to give the address in Memorial Stadium. That was his doing. But he has a very complicated legacy because of his work in a number of different areas. Perhaps the most illustrative fact is that he's clearly the archetype for Dr. Strangelove. But at Berkeley, he loved to teach introductory physics. As time went on, he became a little bit less formal and a little bit more enthusiastic. But his course called Physics 10 is very, very well known. If you talk to somebody from that 70s, early 80s era, more than a third of them will remember Physics 10. And of those people, roughly half will remember it fondly. So he was a real presence because he managed to bring it to a lot of people. He managed to teach a course that was relevant in a very large way. He talked about the issues of the day. And then when he retired, things changed. This is a physics talk, so there will be data, but there will be no quizzes. The enrollment dropped precipitously. And right around here, the department decided that they would give it to a new person. There were some other people involved here. And a course was created known as Physics for Future Presidents. I was, just in the interest of full disclosure, this was entirely done by Rich Muller. I had no involvement in here. I'm the one who sort of made it go like this over in the part we're not going to talk about. So here, although this is not from the very first, so it turns out that if you go back before the invention of the smartphone, it becomes very difficult to find things like pictures of classes and websites and things like that. We have very few surviving pieces of Abraham Lincoln's original website. So this is not quite from the 2001 website. This is from 2006. But I'll try to sort of give you the provenance of these kinds of things. The course was listed as, the title is serious. The course is cross-listed, sometimes called qualitative physics, but it's not trivial. You'll be learning material that's generally not learned by the physicist until after earning a PhD. I can tell you that that's not entirely true, but it's very close. you should come away with the feeling that what was just covered is important for every world leader to know, except for relativity, which is at the end. And this is Rich Muller who created it. This is Rich. And this is in Pimentel, just a little ways over there. And you can see a bunch of stuff on the boards behind him. What's not on the boards behind him? Those of you who hated your physics class in high school or college, what's not on the board behind him? No equations. That's not an equation. That's a definition. This is an equation. This is someone who I've blurred out in one LeConte, proving the proposition that satellites go around the Earth. For those of you who've taken enough physics classes that you can't get them out of your head, this is about gravity, and this is about motion, and this is about pendulums, and there's actually one little diagram here. There's a circle. And this is the traditional way of teaching physics. And if you want to be a physicist, this is your lingua franca. This is where you start, and you might as well get used to it. But the vast majority of the world does not want to be physicists. And the vast majority of the world does not spend a whole tremendous amount of time trying to calculate to 3 significant digits exactly how all this works. It took us thousands of years to figure out that things could go around the Earth. We made a lot of mistakes in the meantime. But once we figured that out, I can convince you right away that it happens by showing you. I don't have to do all this math. And in fact, when Rich polled the students, now, a little bit of history. Some of you look a little young, but not that young. When does school at Berkeley start? Roughly the end of August. So if you polled the students at the end of August 2001, what do you think they would be most interested in? I find this fascinating. 9/11 has not happened yet, right? That's why I stressed August. 9/11 was still 2 weeks in the future. That's the results. So with 9/11 2 weeks in the future, this is what the students came up with. So apparently our students are a little more well-connected than we think. This next one, and we'll talk a little bit about how that becomes physics that you can teach. This is from almost like a memoriam that Rich wrote a couple of years later, and I want to place it as a starting point for how you think about your involvement with people. Because again, in a funny way, this is meant to be an appreciation of all you. Liberal arts students do not much mind learning numbers and facts. They are empowered when they know things, such as what happened at Chernobyl, how many people died of cancer at Hiroshima, what satellites can really do and not do, what Moore's law is, and what the differences are between MRIs, CATs, and PET scans. I tell them that whatever their point of view, knowledge will help them. They win arguments with their friends and parents. They seem to be particularly happy about the latter. Of course, it's also conceivable that they learn the facts. Some students will change their minds on some technological issues. So those are big questions. Those are not equations questions. At least we don't know the equations for them yet. But this approach is just revolutionary for students. There's a story here, which I've never found written down, but I'll tell you now. 2 years into the class, one of the students came back from Thanksgiving and said to Rich that she had been having dinner with her parents and some of their friends, and one of their friends was a politician from Southern California, and topic came to how much solar power, whether solar power is practical. And we'll talk more about this later on. And the person from Southern California said, well, it'll never be possible because you'd have to pave 60% of California with solar cells. And the student says, no, it's more like 10 square miles. And the person goes, now remember, this was before you could look up everything on a cell phone, right? And there was some back and forth, and finally the person said, well, yeah, you're probably right. And here's the part that Rich just loved. And the mom looks across and says, did you learn that at Berkeley? And the kid says, no, I just figured it out. Which was sort of half true. Because it turns out that there's a dictum from Einstein that he never knew the speed of light because he could always look it up. But for the rest of us, that's not actually a very helpful thing, particularly, yes, pre-cell phone. So the course has people memorize things. It has people learn, maybe not to 3 significant digits, but that there's a difference in the amount of energy in an auto battery, a computer battery, and a flashlight battery. There's a difference in the cost of that energy. That explosives have certain amounts of energy in them, but so do other things you can burn. We tended to work, the students tended to go through that. Even when equations were used, they were very simple, just to sort of get the basic dependence. Just say, yeah, that depends on mass, or that depends on velocity. But it would always be done in terms of, well, your energy, if you're moving at 20 miles an hour in a car, is sort of the equivalent of falling 15 feet. 20 miles an hour, you've been in a car, you've thought it was slow, you really wish you could get to where you were going, but you've never really wanted to fall 15 feet. And 80, well, that's really, really fast, but 240 is really, really high. I actually don't know how high the Campanile is, but I suspect it's about that high. So trying to bring these things down because numbers matter. There's a sort of scale, they're factors of 10. Understanding how hard things are matters. I'll give you an example. There was a recent, I just happened to be reading Berkeley side, and I made a strategic error. I was reading the comments after an article, and somebody said, why don't we just put all the power wires underground? It should be easy. Well, in the article was the fact that it costs about $1 million a mile to put power lines underground, and there are 100,000 miles of power lines in California. So maybe 1 mile would be easy, but 100,000 miles is not. And you can do this in your head. How many, real quick, how much money is that? $100 billion. How much money is that for Californians? $3,000 for every man, woman, and child in the state. These are Physics 10 calculations. These are Physics for Future Presidents calculations. Up here is, unfortunately, we only have the slides that were taken, the pictures of the boards that were taken by people who were not obsessive about selfieing everything in the entire world. And this was the grading scale, and it was not graded on a curve. Because, and this is a personal bugaboo that I could talk about forever, if we're trying to build a community that's trying to reach accomplishments, we should actually value accomplishment and mastery. We should not necessarily value getting in front of the kid sitting next to you. So this is a week. Various units of energy, substances, the fact that there's actually more energy per pound in cookies than high explosive. Believe me, I know this. Electric car hype. This one is from 2004. Electric car hype and hybrid non-hype. This is the first occurrence in these slides and things that I want to show you about this idea that our understandings can change. And in particular, the way we present those understandings can change. It's hard to think back to how we thought about cars 16 years ago, and I haven't been able to do very much of it, but I think it probably was hype at that point. I think there was probably still a lot more to be done. Hydrogen as a means of transporting energy. At that point, we had a Department of Energy chief who thought you could mine hydrogen. Uranium, gasoline, and TNT, cheap coal, and the problems that will come from that. I'm going to talk about climate later on, but one of the things that is difficult for students in a traditional course is how sequential everything is. We're going to do things once and then never come back to them. But in real life, that's not how it works. In real life, how you make energy is associated to climate. Climate is associated to fire. It's not really associated to earthquakes, but natural disasters and how you respond to them are connected. All of this stuff is connected. And you don't get to just take one piece out and analyze it by itself and be fully effective. You need to be able to think about these things together. We get all the way down here to power in terms of horsepower, human power, solar power. This goes back to the cookies and various kinds of other things. This was a time, incidentally, when anti-ballistic missile systems was considered a really big deal. and he connected it to the demise of the dinosaurs. You guys know about the controversy over the dinosaurs? There are people at Louis Alvarez and other people here at Berkeley, but Walter Alvarez, believe that an impact of a large body, like an asteroid, disrupted the environment enough to kill the dinosaurs. Other people believe it was volcanoes. Other people believe it was just the Disneyland thing where they all dried out and died. There's lots of scientific evidence that is very complicated. We are still working on this, and there are still people who believe in all of this. But in the meantime, they've made movies about diverting asteroids from hitting the Earth, some of them good movies, some of them bad movies. They've even made Doctor Who episodes about diverting dinosaurs from hitting the Earth. So the whole thing is very based on physics. Here's the Physics 10 version of that slide with all the equations. Stuff goes around the Earth. You don't need to know the equations. But there are some things that you probably should know. If you were back at this time, the vast majority of you, particularly those of you online making me nervous, can probably pull a device out of your pocket right now and get a picture of where you are very, very quickly. But 20 years ago, that was actually much harder. 20 years ago, not even getting it in your hand, getting the pictures was hard. But there were TV shows that would show people, quote-unquote spy satellites, looking in through a window and checking what a piece of paper that was on a table. And if you're going to be a president or even a governor, you better not believe that's possible. It's still not possible. And part of what we were working on is trying to help people understand that satellites that are very low down, and so they're close and so they can see, are moving very, very fast. They go all the way around the Earth in 90 minutes. They don't stay in sight for more than a couple of minutes. They can't watch you for days. But the ones that can sit and watch you or feed your television are 24,000 miles away, and that's a really long way. 24,000 miles is a really long way. It's hard to see anything from there. And this is something that can actually be demonstrated with colored chalk. I will now, at this point, complain about the fact that we're no longer allowed to use colored chalk, but I have some in my bag. Oh, wait a second, this was videoed. Oh, okay, that's mistake number one. We also talked about, we would talk about GPS and how it worked, and what you need to know about how it works, and that it's not magic. There are things that can happen and things that can't. This is Roberta Barreto, who was very, very patient with all of us about putting up demos and showing things. This is this same bag that was here, right here, which is a little distressing too. This picture is from 2009. In the class, there were a lot of demos. In a normal class, it's actually very hard to make the connection between a quick, beautiful demo, maybe with some fire, maybe some accidental smoke, maybe some intentional smoke, and those equations. That connection is very hard for the primate mind. We just don't do that normally. But when you're showing the phenomena you want them to understand, that's different. Right? If you show a video of a satellite going over the head, you don't have to get to the equations. You've shown the most important thing. And so these were critical to the understanding. And up here is the question. Explain why a spy satellite needs a really big camera. That's the next step of this. It's very far away. And in order for it to be able to see very clearly very far away, it needs a really big lens. Unlike this little tiny lens here, which is only useful for comparatively close. I want to talk a little bit about electricity. Electricity has a whole bunch of stuff in here about magnets and monopoles and records and hard drives. These are almost gone now. Motors. And only down at the bottom did we talk about power. But power was a big part of how it works. And this is a very simple model of how power in the large works. You feel very comfortable, but you put a battery in your flashlight and good stuff happens until it stops happening. And then you put another battery in, or you replace the flashlight, or you send your teenager off to do it. I'm losing my last teenager tomorrow. I have my youngest kid has his 18th birthday tomorrow. So, yeah, exactly. But power is made in a generation station. It travels over high voltage lines. It gets made lower voltage, lower voltage, lower voltage, and finally it runs through some little tiny poles and it comes to your house. So it's very apropos that in the last couple of days, this system has broken down. Over the last month, it's broken down a couple times. The problem, of course, is that you don't necessarily want to have that power plant in your backyard. They're big and they're ugly and they make a lot of heat. And in fact, they serve a big part of the world. One of my first jobs getting out of college was working on a dam that provided enough electricity to power a quarter of Los Angeles. So it can't be in somebody's backyard. But this is a very fragile set of pieces. These are just little tiny bits of wire that connect all these things together. Now, one of the nice things about Berkeley is that stuff's happening all the time. So I forget the year of this, and I didn't write it down. We even got to go to a field trip to a blown-up substation. You recognize where this picture was taken? It's in between. This is California Hall over here, and this is Durant Hall, and that's the library, and Wheeler is here, and this is Campanile Way, and this is the exploded substation that's buried in the ground. I made a mistake. I was teaching a class this semester. I made a mistake. I told the students that they should go look at this. There were 580 of them. I got a nice note from the then head of facilities that really I shouldn't do that again because they were trying to get it fixed. This is a slide from, I think it's got the date in the corner, 2009. We actually use this slide for a couple of different purposes. One is to show you how you can give a misleading thing. This line across the top is colored average load. It's the amount of electricity that the state of California consumes as a function of time in the day. So at midnight, it's pretty low, and then as morning comes around, it rises up, and then about 5 or 6 at night, it's at a peak, and it drops back down again. And this is labeled as, now again, 2009, this is labeled as solar. And it looks like it's like a really big fraction, right? You can see that, of course, solar power peaks in the middle of the day. It's pretty much negligible at 1 o'clock at night. It's pretty much negligible at midnight, although it does manage to get a little bit of time there. But it looks like, wow, that's like a third maybe, except that this is on this scale. So this peak is 50,000. And this is on this scale. So this peak is 1,000. It's not, at that point, in 2009, it was not a big effect. It was not a big part. The other part of the argument that was made by this slide is that this is wind power. Most of the wind is at night, very little in the day. We tend to be calm here in the day. And that those two sort of work together and were flat. And I'm a little color challenged, but I think there's a line sort of where I'm pointing at. That's how much, that line is this line minus all of this stuff properly. So this is what had to be provided by thermal power burning gas and coal and oil, plus hydropower from the Pacific Northwest, most of it. But remember I talked about how time advances and how our understandings change. California has worked very, very hard to put wind and solar power in place. And we've gotten now something called the duck plot. I say that so that you'll see it when it first pops up. Right, it's a duck, right? It's obviously a duck. Again, this is time across the bottom. And what's plotted here is the amount of power that is being produced by hydropower and thermal power plants. In other words, we take solar and wind out. And in 2012, we had made enough progress since 2009 that, that big rise at 5 o'clock was being used by solar. And that was cool. And as more and more solar is being added, we have to generate less and less solar power. And this is actually a 2014 plot, but these turn out to be pretty much true. Less and less here. But the life of electrical engineers, the people who live in the buildings right here, is always very, very complicated because turning on your power plant that fast at the end, it's not like flipping a little switch. These are gigantic things, and they take a long time to do. And of course, as soon as this goes negative, you've got a problem. So these are the kinds of things that lead to power distribution networks that look like this. You recognize California, of course. The color coding is a little bit chaotic, but the big dark ones are huge power lines that bring power from the Pacific Northwest, bring power from Arizona and Nevada, This is us. And this is why we've been being blacked out recently, which is that power comes into us from behind. The little tiny generators are not sufficient to actually feed us all. And there are the power lines that actually feed this part of the bay are either coming up along here or are coming through a very windy part of California. So if we were teaching physics of future presidents right now, this would be a 2-day unit to work through the physics and technology of this thing that's going on right now and try to predict 5 years forward for what it is. Here's a blow-up of that plot. The coloring is even worse, and wow, that did not come through very well. These are the major substations. These are the places where the highest voltage power is knocked down. And so this is the place where PG&E gets to decide what turns off. And so they don't have a whole lot of granularity. When they decide to turn off, they're turning off all of this stuff because that little nerve ending there has to feed all of this. And there's only one choice of path between this part and this part. If anything goes wrong on those lines right there, we all go out. The other part of this is coming back to this same picture is the last little bit. This is a picture that was from Physics 10 when it was being done. And we teach people about why poles are like that. Not so they can engineer them themselves. Not so they can go out and fix them. God awful that would be. Certainly not so they can go out and connect onto this one, not this one, to steal power, or cable, or telephone. Not that you would. But to give a sort of understanding of what's going on in your neighborhood, what's actually there. And then, of course, this is the reality. This is, I think of this as my pole. It's near my house. You know, you can imagine that this is a complicated thing to work on. We don't actually shy away from these courses. You know, your students are quite capable of thinking about difficult things. So if you're thinking about power, you're thinking about nuclear power too. You're thinking about risks from that. You're thinking about dangers from that. You're thinking about the fact that certain amounts of radiation can kill your cells, can give you cancer, can kill you. That there are several different kinds of physics and biology that combine here in different ways, that it is a quantitative thing. But after working through this stuff at a remarkably fast pace, because we're not spending 10 years making them physicists. We're spending 14 weeks. We can get to ideas like they understand these things, that gasoline is a very potent explosive. Although cars don't blow up the way that they do in TV shows. You have to work really, really hard. This would be a great demo, but we never actually do it. Dirty bombs, if you'll recall, remember, terrorism was a thing even before terrorism was happening. And it was very much, for the first 7 years of the course, it was very much a part of the course that the students wanted to know more about. The scenarios were scary. There was a final exam in 2005 where they worked through setting off a nuclear device in Berkeley and worked through what that would mean. And that's a hard thing to think about. But our students are remarkable. And times have changed a little bit. If we were teaching this course in this same way today, there would be different issues. I think we might use slightly different examples. We might have why 737s are not flying today. But some of this stuff is actually still on point. And, you know, one of the things that's nice about this institution, maybe nice is an understatement, is that together, all of us, faculty and staff, people working in many different disciplines, are figuring out what that new future looks like. Right? We do sort of work 5 years in the future at what we're doing. The students love this. The students love it so much that in 2008, they gave it a Best of Berkeley award. I particularly love this because I started teaching the course the next year. And I have tried 3 times to get this to reliably show, and I can't do it. So I need a teenager to help me. But what this is, you can look it up. Look up on YouTube, look up Rich Muller protest reply. And you can see a little 5-minute video taken in Pimentel Hall taken by a cell phone, of protesters coming in and demanding that these students join them for their particular protest. This is in 2010. Rather than argue, Rich says a very simple thing. He says, we're going to learn about tsunamis today. We are working our way through the impacts of tsunamis and earthquakes on Malaysia. You've done the readings. Have to talk. We want to talk about it, but if you want to go, you can go. I won't watch. And he turns his back for 30 seconds. What do you think happens? Nobody leaves. Well, unfortunately, these guys didn't leave. But eventually they left. Because the students perceive this as value. Right? And what we all do, what you do, is perceived as valuable because it's the education of the students. I want to talk about one last topic, and then we'll take whatever questions where I was unclear. What do you think that is? Aside from poorly drawn. This was my drawing. Aside from poorly drawn. Well, that's a car. That's me. That's a car. That's a tree. That's another tree. This is the sky. This is frost. So, have you ever noticed that if you park a tree over your car, now, geez, okay, that's two. Cars that are parked under trees, I wish the drawing was better, don't get frost on them in California. And on a clear, beautiful, see the sky night, cars that are not parked under trees do. Why is that? Well, first off, once you get it, you understand global warming. Trees are hot. Sky, not so hot. On a brilliant, cold California night, there's no water in the air. And all the heat that's being given off, that's being radiated away, radiates up into the sky. Here, you have a car that's at, room temperature, 40 degrees, 50 degrees. And you have a tree that's at room temperature, 40 degrees, 50 degrees. And they just radiate heat back and forth. And they all pretty much stay the same way. But the reason the desert is cold at night is that nothing keeps the heat in. Nothing keeps the heat from radiating to space. Okay, so if it's a cloudy night, why does this not happen? It doesn't get cloudy in the desert. That's why it's a desert. But on a cloudy, foggy night, it doesn't feel that cold here because there's a cloud that acts like a tree up here. The water in that cloud might be a few degrees colder, but it's not the coldness of interstellar space. It's going to radiate heat back down. They're going to be in equilibrium. If you put carbon dioxide in the air, it does that too. And it radiates back down, and it makes things warmer. That's all there is to it. We like to talk about the greenhouse effect. How many of you have ever actually been in a greenhouse? Oh, more than I thought. Maybe that's a California thing too. So 18-year-olds have generally not been in greenhouses, unless they're growing pharmaceuticals, but that doesn't count. So here's a sort of unfocused picture of that same thing, but instead of talking about the cloud, we talk about the glass. The physics of that has to be put in a context, though. If you want to think about, if you're trying to get 18 to 20-year-olds to think about not just the physics of carbon dioxide in the air, but what that means, you have to put it in a context. And this is a slide from 2001 that has, as a function of time, from 1900, so this is basically a century of how much CO2 is being emitted per year by Japan, by Western Europe, by the US. Eastern Europe is here. There's some interesting structure to these things. And then mostly India and China, going like that. And here are the spring 2003 quick facts from this course. Carbon dioxide warms the earth, that's true. Global warming is real and a true threat, but many claimed effects used to illustrate global warming are grossly exaggerated. Hurricanes and tornadoes are not increasing, nor is the number of U.S. wildfires. an interesting slide to put up today. You'd think I might have edited that one out. So did I think about editing it out. But remember, part of what the university does is to figure out the best truth we can, and that changes over time. In fact, in the book, and unfortunately I do not have a copy of the 2002 book. I wish I did. It wasn't a real book. It was a course reader book thing. There's data to show that that's true. That's changed in the intervening 17 years. That's not true anymore. The Kyoto Treaty was the big thing at that point, but as we saw on the other time, you can interpret that data. You can learn to deal with this data, and in fact, there was some numerical work we did. But you can also see that the students are being presented with the real data right up to the time that we know how to interpret it. A couple of years later, this was being shown. This actually takes a little bit to think about. This is sort of how much the average person income is. And that's hard to evaluate from one part of the world to another, and that's really sort of economics. It's not really physics. But we trust our colleagues to come up with something that they believe. And then the total amount of energy that's used here. America is a very wealthy country, and it uses a lot of electricity. India and China, not so much. They're not very wealthy, and they don't use a lot of electricity. The points are just points. But it turns out that almost all of them, as a function of time, are going this way. So over time, countries become both more resourceful, more wealthy, and also using more electricity. There are three features of this, aside from the awful color code. There are three features of this. Let's see if you notice them. What would you say about, pick two countries that are striking, and tell me which two they are. Well, some people will immediately go to these two. What's going to happen with those? Right? Almost 2 billion people, more now, are going to want to be up here somewhere, which probably means they're going to use, well, somewhere in here, worth of electricity, worth of power, and that's a lot of emissions. Another one is these two seem to be on a different line. And Russia and the US, you don't necessarily want to tie them together, but they do seem to be on a higher line than everybody else. And that seems to be due to they're the ones who built steel plants and cement plants and things like that before everybody else did. They industrialized in a different way. And the United States is trying to get back down, and if we have this plot more recently, in fact, we've come down significantly. And some manage to use less electricity. It can be done. This is sort of where Physics for Future Presidents signs off, because we put a bunch of things in our students' hands. We've shown them how to think about things. We've shown them how to be quantitative, how to look at what's possible and what's not. But we don't have solutions. We have the next generation of students. Now a book was eventually written. Rich Muller has tried very hard to get this into the physical hands of presidential candidates so he can get a picture. They've all been smart enough to not do that. But this is the entire coverage of the thing. You can see that by the time we get down to these, we have worked our way through a lot of different stuff that we can tie together. And we end it with a few pieces, the relativity that you saw mentioned before early on, about how science is not just about building things and keeping things from getting better and worse and sideways power plants, but some of it has an intrinsic beauty. And I'm going to do that really quick. What is this? What are you looking at? Not me, that. What are those little... Okay, what are galaxies? Bunches of stars that are sort of bunched as stars in bunches. How do you know? Yeah. How do you know that those big fuzzies, there actually are a couple of stars. That's a star, that's a star, that's a star, and there's one more here that I don't see at the moment, but I know there are 4 of them. But all the blobby things are billions and billions and billions of stars. But the question is, how do you know? And that's the fundamental question of the practice of physics itself. How do you know? How do you know how the sun burns?
Is it the shape? Is that the shape of that?
Good question. This is a Hubble Space Telescope photo. The raw image, the full resolution image, is incredibly beautiful. Right? It loses a little bit being projected out of a laptop. This is one of the first pictures. This fuzziness is because it was digitized, but the whole thing is basically fuzzy, of galaxies. One of the very first that had more than one on the plate. It's almost exactly 120 years old at this point. It'll be 121 years old on Saturday. And nobody knew what those were. This is a picture of Lick Observatory. You know where Lick Observatory is? It was built by the University of California when there was only one University of California. Now we have Santa Cruz, we have Berkeley, et cetera. It's near San Jose. It's in the hills over San Jose. This is the telescope. These are people for scale. You notice they're wearing hats inside. So we laugh about coats and ties while teaching. They're wearing hats. Big telescope. And with that telescope, they were able to start to get good pictures and to believe that this was somehow a combination of stars. Now, if it was just a glob of stars that were just glob-like, they would go plump and collapse onto each other. Right? They would fall under their mutual gravity. So they must be spinning. If that's a bunch of stars that's lasted for more than a couple of thousand years, they must be spinning. Must be is not a verb in the physics vocabulary. Must be is a recipe for somebody's got to check that. And so the way you check that is you measure what one side or the other of this thing has to be going toward you and the other one's going away from you. And using what's called spectroscopy, Doppler shift, you can measure very accurate velocities and you can determine that. You can even do it for slices. You can measure here and here and here and here and here and here and here. And what you get is that as a function of distance away from the center, here, 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 the velocity toward or away from you looks like this. Which is great, except that we were predicting that it would look like this. So we know it's spinning, but there's something about the way gravity works, or something about the way the matter in that galaxy is organized, or something about extra stuff, or there's a new mystery. Physicists are very, very good at keeping themselves busy with new mysteries. In fact, if you're a really good physicist, you'll solve one and create 2. Better pictures, which are not just glorious, but better, enable these experiments to be done in more and more detail. And this is work surprisingly recently. The date on this is 1979, which I consider to be surprisingly recent, by Vera Rubin and college. She was actually our graduation speaker at physics a couple of years ago, where they did this a whole bunch of times, and 21 galaxies, and they determined that there's something in these galaxies, there's actual stuff in these galaxies that we really don't understand, we really want to understand, and we need a word to refer to it, so we're going to call it something really, truly glamorous. We're going to call it dark matter. Physicists are not good at naming things. Astronomers are even worse. And we have new pictures. You can see, it's really hard to see as it gets projected, but you see sort of rings here. That's the way the light is distorted by the mass that is in here. It lets us measure this lots of ways. At Berkeley, we're actually building a couple of different kinds of experiments to look for these things. We've been doing it for almost a decade and a half now. We're not finding anything. We're not detecting, so it's seen in the sky, it's not seen in the lab. This is great. Dark matter detector finds nothing, so why are the scientists happy? This is from the LA Times front page. There's nothing that makes an experimental physicist happier than proving a theory wrong. Right? Nothing makes us happier. The second choice is being able to understand the world and talk about power plants and talk about all these other things. But if you can say, oh, that theory is wrong, You just do a little happy dance and you go back to the lab, because by the time you get back to the lab, the theorists have come up with 3 more theories. Remember the part about you kill one and you get 2 more? They're very good at that. But part of what we do at Berkeley, we all collectively do, in our labs and in our classrooms, is create that new knowledge that our students are going to suck up. I mentioned Space Science Laboratory builds satellites. They were only peripherally involved in this, but this is China launching a satellite to look for this stuff. The date on this is December 2015, and the reason I love this, I actually took this picture. This was a newspaper that was down by free speech. What's the most thrilling thing about having an above-the-fold physics experiment in China daily? What really adds to that? It beat out the new Star Wars movie for publicity. But despite all that work, here's what we know about dark matter. But we're learning. Okay, let me summarize. Let me come back to where we started. We teach future leaders. We teach them history, we teach them physics, we teach them economics, some other things they have to learn by themselves. And they go on to be these people. But really, this is about the future presidents. Really, it's about these people. It's about the ones we have today and we will have later. And so I'm here in Appreciation Week to thank you for all you do to make this institution able to do that, to bring this new knowledge and help these new students become who they want to be. And with that, from the bottom of my heart, thank you. So I ran 1 minute long. I'm out of practice, but if we have questions, I'm happy to try and answer.
The slide that had income, I think it was income versus electricity?
Yeah.
Or power?
Energy in general.
Okay. Why is Australia so high? What's going on in Australia?
So Australia is a surprisingly industrial economy. They have a lot of what we would call heavy industry, steel and doing stuff with coal and stuff like that. And you think of it as, boy, I hope there are no Australians here. Yeah, okay. I forgot about all the people online. And I hear them screaming. Do you know who Terry Pratchett is? He was an author of a bunch of books. And his books talk about a particular culture, and there's a library in there. And there's a huge multi-volume set of books there, which is basically dangerous animals in Australia. And there's a little appendix which is not dangerous animals, which turns out to be some sheep.
Okay. And they're not native.
Yeah. So, that's what we think about. We think of Australia as beaches and otherwise, but it's mining and heavy industry. And it turns out that those are the same things that particularly push Russia.
So it's not air conditioning?
It's not necessarily air conditioning.
Okay, that's what I was wondering. All right, thank you.
Yeah, you know what the biggest single user of electricity in California is? Moving water. Yeah, somebody knew the answer. Moving water. The electric pumps that move water around the state for, the central aqueduct that you see as you go down Route 5. So this is country by country. So I don't know that any individual country in Africa was big enough to actually be surveyed. So I don't know the answer. The question was, where's Africa? And the answer is, it's south of Europe. But I don't know where it would be on here. I suspect it would probably be down in here.
Even South Africa?
I don't know.
It was really interesting to see the class material from, I guess it was 17 years ago, saying, oh, it's a little exaggerated, all this climate change business. Do you feel like there's something like that right now, something where the ground is shifting?
So it's a feature, perhaps of human nature, which I am not an expert on. I only have a sample of one, that in order to get things done, people tend to exaggerate a lot. And if you're working on the science, you have to be really careful about that. Because on the one hand, whether it be climate or fire or the future of power, there's just so much that you don't know, right? We live in a very, very complicated universe, a very complicated world. There's so much you don't know. But once you've been working on this stuff for a long time, and dark matter, which that was my part of this thing, nobody cares, so that's fine. But if you're working on some of these other things, it's not really exaggeration. It's talking about a realistic worst case. Most worst cases don't happen. But if people don't understand the worst case, they might not actually deal with the realistic case. So I don't know. I think that's a very hard thing. But it doesn't help if someone says, well, the facts indicate A, B, C, and you can pull out a plot and show that's not true. Right? That doesn't actually help society get to where it needs to be. So in 2002, when famous politicians said that hurricanes had quadrupled, and you could make a plot that showed that wasn't true, it made it very difficult to figure out how we deal with these things. I can understand the urge to point at the worst case. But there's a difference between the worst hypothesis in the future and misstating the past. Yeah, one more question? Because I'm going to sneak in one more. I'll go here. And Avi, I'll get you after.
So I guess with the changing world and changing understanding, with changing world, changing understanding, how do you decide what goes in the course, and how do you keep up with what's,
So I'm not currently, oops, I wanted to go one more. I'm not currently teaching it. And so I don't want to comment on what we do at the moment, right at the very moment. But one way of teaching these courses is to sort of work at several different scales. So take the first 10 minutes and just listen to whatever the questions your students have. That's a terrifying thing to do, whether you're doing it by listening to people who are about to ask you a question and you might not know the answer, or in a classroom or even in a bar, because you might not know the answer. But you can work it out and you can come back, except in the bar, well, even there. And sometimes you can't even work it out. Sometimes it's a question that nobody knows the answer to, that we don't even know how to start on. But it's not that hard to follow the students' instincts. They really do have a good sense of what matters. You don't necessarily trust their details, but the topics they're interested in are important. Right? You are arming them, we are arming them for what they're going to do 5 years, 10 years, 20 years from now. They know better than we do what that's going to be. Okay, that's actually sort of a downer to end on, but that's where I'm going to end on anyway, because that's just who I am.
Thank you so much, Bob. My name's Angela Stopper. I'm your Chief Learning Officer here on campus, and on behalf of our CHRO, our Chief Human Resource Officer, Eugene Whitlock, who opened us up, on behalf of me, all of us at Central HR, the People and Organization Development Team, I just want to close us up by saying thank you again. Thank you all for everything you do. Those online, those who are watching this in the future, thank you for everything you do to make Berkeley the great, wonderful campus that it is. One more round of applause, please, for Bob, our wonderful speaker. I hope you've enjoyed the Fall Staff Appreciation Week. I was chatting with James Dudak, who is our Employee Experience Lead. This is our third Fall Staff Appreciation Week, which means it's a trend now, I think. So, yeah, so we're going to keep on doing this and appreciating you, not just today, but every day. So thank you so much. For those of you that did sign up for the stretch that had to be canceled because of weather, James has assured me that's been rescheduled, and you've all been let know when it will be. So sorry for having to cancel that because of the weather, but we have gotten that rescheduled. And once again, thank you so much for all you do. We really appreciate you.